This is the second lesson on building the software. In the previous lesson, we talked about the concepts of sections and symbols. In this lesson, we look at the actual process of doing a build. We'll start by looking at the tool chain. Now, the term tool chain is just a fancy word for the set of tools, like the compiler and linker, that you use to build code. Following this, we'll look at the overall build flow, starting with source code and ending with the image file to be programmed into Flash. Here I think the term tool chain will become more clear as you see how the tools are used in a step-by-step process, like the links of a chain. Finally, we will look at some example input and output files relating to building the software for this course. We'll look at the linker script input file, which gives the linker information about our board's memory and how sections map to memory. Then we'll look at the build console output text, which is a great resource to see what the IDE is actually doing. I've used this countless times. Next, we'll look at the map output file, where the linker writes information explaining what it has done. And finally, we look at the list file, which shows how your C code was compiled into assembly language. So we need a set of tools to build our code. Most notably, we need a C compiler and a linker. The IDE takes care of this for us, and it uses the GCC toolchain, also referred to as the GNU toolchain. This toolchain supports many processor architectures, including ARM, which is what we need. A major part of the processor architecture is the machine instruction set. Now, because there are different versions of the tools for different scenarios, a command name prefix is used to avoid ambiguity. The prefix is made up of several terms separated by dashes. And here is the general format. Because the vendor term is not always used, there is a second format that doesn't have the vendor. So what the terms mean is listed here. Arch is the chip architecture like x86 or ARM. Vendor is the supplier of the tool chain, which could be something like Apple, but this term isn't always used. OS tells the operating system that is the target, and it could be something like Linux, or in our case, since we are bare metal, it would be none. And then the ABI is the application binary interface. An ABI is a set of rules for how variables are laid out in memory, how function calls work, and other low-level details. There are sometimes several ABIs for the same architecture. For ARM, there is an ABI for embedded called eABI. Now, for the course project, the tool prefix is ARM-none-eABI. And this should be fairly obvious from the description I just gave of the prefix. So that means the compiler, which you normally think of as GCC, would actually be ARM-none-eABI-GCC. I need to emphasize that this is a cross-compiler, and the prefix refers to the destination or the target of the code, not the machine you are using to do the build. In my case, that is Windows. So there is a different version of ARM-none-eABI-GCC that would run on Linux. Now the IDE installs the tool chain for us, and it's well hidden. And here is the path on my Windows laptop to give you an idea. By the way, note here that in the rest of this lesson and the course in general, I used the tool names without prefixes just for brevity. So for the compiler, I would just say GCC and not, this long name. So I've been holding off on this diagram because it's a little scary, but this is important to understand. It is the high-level view of how builds work. It starts with source code at the top and ends with an image file ready to be programmed into MCU Flash at the bottom here. These blocks of different colors represent different kinds of files. The text in the box tells you what's in the file and the file name extension. The arrows between these boxes shows how one set of files results in the next set, and the tool used to do that is shown in red. These tools are part of the tool chain. So let's start with the main source files. In other words, the .c and .h files that you wrote, or files that were generated by the IDE. Notice I include in these the .s extension. This is for assembly language files, and in this course there is just one such file. It's supplied by the IDE, and we will be reading it in a future lesson. So our source gets compiled into .o object files using the GCC compiler. Normally there is one object file for each source file. The object files contain the compiled object code in a symbol table as we just discussed. Now let's go to the second column. This is a similar chain that is used to build archive libraries. We tend to use libraries to help organize large projects, or possibly to conveniently share code between projects. We don't actually build any archive libraries in this course, but we could put some of our code in libraries if we wanted, and this shows how we would do it. As you can see, we compile the library source files like we did before to get a set of object files. Then we use this AR tool to package these object files into an archive library, which is .a. An archive library is just a file format that holds a set of object files. It's a little like a tar file or a zip file, except that it is not compressed. Now the third column shows pre-compiled libraries. People in embedded often don't like pre-compiled libraries. We tend to be control freaks where we want the source for everything so we can look at it and build it ourselves. I bring this up because with STM32Cube IDE, the standard C libraries are provided pre-compiled without source code. This fourth column is somewhat obscure, but I'll include it for completeness. It is called the C runtime. This is code that is very tightly tied to the compiler. It is used for special operations like during the startup of a program. You will sometimes see file names with the letter CRT, and that stands for C runtime. It is unlikely you'll ever have to deal with these, but it is good to know. So now we are down here. We have all the object files, either standalone or in archive libraries. We use the linker to pull it all together. Now, the actual linker tool is called LD, but the GCC compiler can run the linker also. So often you will see GCC being used to do the link. You'll see coming in from the left another input file with a LD extension called a linker script. This is linker instructions that you write. Now for this course, the IDE is supplying the linker script, and we will be looking at this file later. It generally tells the linker about the memory map of the system, like the starting and ending addresses of the flash and RAM. The linker needs this information to map object code and variables to memory. So first the linker grabs all of this object code that was specified. Combining that object code, it checks if there are unresolved symbols. If there are, it needs to look in these archive libraries. An objective of the linker is to minimize the amount of flash and RAM memory used. So it goes through the archive libraries and looks at each .o file to see if it contains an unresolved symbol. If so, it pulls in that .o file. Now, the object file just pulled in might contain other resolved symbols, so this is an iterative process. But the idea is that the linker only pulls in the .o files that are needed. We assume that eventually there are no unresolved symbols. At that point, all object code and variables will be mapped to memory. The linker can edit the object code to fill in addresses and produce true machine code. Now, the linker generates an ELF file for the entire image. This ELF file contains a lot of information but isn't in the right format to program into Flash. We need one more step. The Object Copy tool can take the ELF file and generate a Flash binary image. This is just raw machine code and is used to program the Flash, where the first byte of this file normally corresponds to the first byte of Flash. I'll say here there are other file formats for machine code. One is called srecords, and you can Google that if you're interested. Now, to the right, I show some other information files that the linker generates or that can be generated with other tools. I put them in dashed boxes as they are optional and for information only. The .map file contains a lot of information about what the linker has done, as it pulls in code from archive libraries to resolve symbols and maps object code and variables to memory. The .sim file produces a simple table showing the symbols and their values. The .list file contains a disassembly of the image file, where the original C code appears next to the assembler code. It is useful for some kinds of debugging or just to see how the compiler has converted C into assembly. I wanted to add one more thing. When working on Linux and Windows applications, we often have shared libraries. They are .so in Linux and .dll in Windows. Shared libraries are linked on the fly when the program is started. We don't use shared libraries in bare metal embedded because everything is linked together in one big image, and so everything is inherently shared anyhow. It is always the case we want to minimize the amount of flash and RAM we use or need. This is especially true with microcontrollers, which might not have a lot of memory. As mentioned earlier in this lesson, the linker does try to minimize usage when pulling object files from archive libraries, but we can do a lot better. The problem is this: the traditional linker works in terms of object files, but an entire object file is included in the image even if only a small part of that object file is needed. The solution to this has two parts. In part one, each function and global or static variable gets its own section. So in this example, we have a file with two functions, func1 and func2. And if we look at the symbol table, we'll notice that func1 is put into section .text.func_1, and func2 is put into this section. So both variables or symbols are global. They both have a value of 0. This is the offset within the section, and they will both have a 0 offset from the beginning of their own section. The key, though, is different sections, different text sections. Now, this enhancement on its own doesn't do us any good, but then we add part two of the solution. The linker has a section garbage collector that removes sections that are not needed. So say this example file is part of the image because func1 is needed. The image will also include func2 because it's in the same object file as func1, even if no one calls func2. But with garbage collection analysis, the linker will find that there are no symbols in this section that are needed. So it can discard that section, which means func2. I gotta say, when I first saw this feature, I was very impressed. It was clever and it was simple. Now we're going to look at some files related to building software. I'll start with the linker script. This is an input to the linker and provides information about hardware and the mapping of sections to memory. This is a file that you could write, but in our case, it is provided by the IDE. It has a .ld file extension, and you'll find it in the project workspace. Now, the linker has its own language, and I don't want to get bogged down in the language or some of the details of what's going on in this file. So I will just highlight a few things, skip over a lot, just to give you a feel for how it works. If you ever need to work on a linker script, you'll have to learn the syntax. I have edited linker scripts from time to time, often just adjusting the amount of memory allocated for certain things. So first of all, on line 28, we see this entry directive telling the linker that the software starts at this symbol called reset handler. We'll see this code later on in the course. This will make sure that the linker pulls in the object file that contains this symbol. And of course, any references from that object file will also have to be pulled in by the linker. The next few lines of interest are symbols that are, in this case, they're the exception. They are not addresses. They are actually sizes, and they are giving the min heap size and the min stack size. Actually, I believe you can, if you're using the IDE, I think you can set these from within the IDE, and then I imagine the IDE will update this file. These entries here are key. This is telling the linker about the memory that's available. It says that you have RAM starting at this address and this length, and then flash. The next section, called sections, is the bulk of the file probably. And what this does is indicates where various sections should be mapped to, what kind of memory. So we start with this section called ISR vector. And we will see the file that uses this section later in the course. But this section contains the reset vector and the interrupt vector table. And here's what's the key thing on these sections. It tells that this section is going into this kind of memory, in this case, flash. Next we have text. That's the program instructions. And that goes into flash, no surprise. The key thing here is this indicates other section names that apply here. And here's a key one, .text star. That's a wildcard, that star. And this picks up all of the text sections when you use the feature we just discussed, where every function has its own section. So this takes in all of them. Read-only data goes into flash, as you'd expect. I'll skip these. These are sort of details, as are these. The next section is .data, and this is an interesting one. As you'll remember, .data is where global or static variables go when they have non-zero initial values. Here is the interesting line. One is this section goes into RAM. Makes sense. Then this other one is a little less clear. It's also putting something into flash, but it has this AT as a special directive. What's going on here is those initial values for those variables have to be stored somewhere in flash, so that when the system boots up, those variables can be set to their initial values. And so that's what this is doing, storing the initial values in Flash. We'll later look at the code that copies those initial values to the variables before main starts. Next we have the BSS section. These are global and static variables where 0 will be the initial value, and those go into RAM as you'd expect. I want to point out something here. This linker script is also defining some symbols, including this, which would be the start of BSS and the end of BSS. These symbols can be accessed from C code and will be used again in some code we'll look at in a future lesson. Finally, we have the user and heap stack, and that's being actually defined here. And these lines here, what they're doing is this dot is the current address. And so they're in that RAM as we're allocating things to RAM. Dot is the current address. And it's just adding the heap size and the stack size. The heap and the stack are just allocated right next to each other, which is fine. Now, if all of your stuff didn't fit, for instance, you overflowed your flash or you overflowed your RAM, you will get an error. And so that is how we find out we have exceeded the amount of memory, and at that point you have to do something. You have to try to reduce your usage or find a chip with more memory. So that's it for the linker. The next file I want to look at is the build console output. This is the text that comes out in the console window in the IDE when you do a build, and I just cut and pasted that output into a file. Now, this is very useful information because it tells you exactly what the IDE is doing to build your software using the GCC toolchain. The IDE we are using uses make and makefiles to do the build. Now, the make tool is a big topic we won't be covering in this course, but it is good that the IDE uses make because that would provide a good starting point if you want to move your software development outside of the IDE. And we have done that on projects in my career. The build output shown here is doing a build from scratch. Now, just before I did this build, I did a clean, which wipes out all of the build output, and so everything gets built. So if you look at this file, the first thing you see in these lines is we are doing compiles. Here is the GCC compiler, of course, with the prefix on it. Now, these compiles have a very long list of options, and I'm not going to go through them. Some of these options are pretty obscure, but it would be a useful exercise to read through these and see what you can figure out from them. I'd like to point out that on one of these lines, I think it is line 19, problem selecting it, it's actually building a assembly file. It's the one assembly file in this system, and GCC can be used to do that as well. Now, line 26 is an important one. This is the link stage, and again, GCC is doing the link stage rather than LD. Now, the files that are being input to the linker are not listed on the command line like they sometimes are. They were put into a list, and then the command is referencing that list. And I have that list file right here, so you can take a look at it. So these are a bunch of object files, and some of these are generated, some of these are from the HEL library, and so forth. So those are the inputs to the linker. And then the linker is also provided some archive library files that it can use. So the linker will generate this MCU class 1 ELF file, and that ELF file will have the machine code and a bunch of other information. Then, just for convenience, the tool runs this object dump and creates a list file, and we'll talk about that in a short time. And then the final thing it does is it needs the output in a raw binary format that can be used to program the flash. And that's what this object copy command does, and it generates the file MCU. Let's see if I can highlight just that file, MCU class-1.bin. So that is a complete build. Now we're going to look at the linker map file. This is created by the linker to more or less tell us what it did. Now this file is huge. It is over 3,000 lines long, and this is a small project. Now I'll have to tell you, a lot of the information in this file is really not too useful to a person. It's related to the debug information that the linker generates for use by debuggers. But it does contain some very useful information. I mainly use a map file to answer one of two questions. Question one is, what is the address of a particular function or variable? And question two is, what object file or library did a particular function or variable come from? In a large system, this is not always a simple question to answer. So you go to the map file to get the precise answer. I'm going to just pick a simple example to show you how this works. So I'm going to look for the symbol hell, or the function, hell_delay. And here we are, and I'm just going to go to the beginning of this line. So these three lines are the useful ones. First of all, the linker is telling us here, I pulled in a section by the name of .text.hell_delay. Notice that hell_delay function got put into its own section based on a discussion we had earlier. This next line tells us where that, what file or what object file that function came from. That's my question number 2. And this value here, I believe this 48 hex is probably the offset within that file of that function. And then finally, this 0800 09A8 is the address in Flash of that function. So that is what I am typically looking for from a map file. There is one more thing I just wanted to show you while we're in here that is interesting. This first part is telling us what archive libraries did the linker pull object files out of to satisfy some unresolved symbol. And I'll just show you the first one. These lines are very long, so I'm going to have to scroll to the end. What this first line is going to tell us, whoops, I didn't mean to do that. What this first line is going to tell us is the library and the object module that was pulled in. So let's go to the end. And this is the archive library, libc-nano, which is also known as newlib. And the object file is this, lib-a-airno.c. This is a very confusing name, the fact that it has lib-a in it. Just think of it as airno.o. So it pulled that in, and why did it pull it in? Well, the next line tells us that. There was a object file called under core source syscalls.o, and it referenced a variable called __airno. And so the linker had to find that variable, and it found it in that archive library. And so that's how it went. This list is really sort of surprisingly short. There would normally be a lot more things, but because this image barely does anything, it's short. So that is the map file. Finally, we'll take a quick look at the list file. This file shows how your C code was converted into assembly. By the way, one thing this file is useful for, is if you're trying to learn assembly language, because it shows you the C code line by line and shows you the corresponding assembly language. I do have to say, if your compiler is set up for high optimization, sometimes the relationship between C code and assembly language is not so clear. Um, but if you turn off the optimization, then it's usually much more clear. So I have occasionally used this kind of file in my career, mainly for one scenario. I get a crash and I have the program counter value. I might have some other information, but if I have the program counter, I can go to this file and see exactly which assembly language instruction caused the crash. So let's do a little example here where the program crashed at 800.18.90. So here we are. Now, of course, I've looked at this in advance, so I am not doing this on the fly. The first thing we'll notice if we go up a little bit is that this is in the HAL UART transmit function. The second thing, if we can trust this relationship between assembly language and C, we'll say we are on this line of C. Now, if I were looking at this line of C, I would immediately see, aha, a pointer is being used. And that's trouble sometimes. I would suspect that there's a problem with that pointer. And by doing a little bit of analysis of this assembly language, I can tell you that this line here, this assembly language instruction, is getting that G state using the pointer. So almost certainly this HUART pointer is bad, and it might be null, for example. So this is one use of these listing files. So that is it for the build process. There was a lot of material in this lesson, and I learned this material over many years. And I had the advantage of, I guess it's an advantage, of starting out programming in assembly. So some of these concepts you learn almost immediately. But if you just get a few of the basic concepts from this lesson, you'll be on a good path. Once again, thanks for watching.